Sine. It's not too painful to differentiate sine, even if we've got to do it a whole bunch of times. Well, here we go. Here's my function. I'll call it f. So f of x is sine x. And now let's start differentiating. So the derivative of f, derivative of sine, is cosine. The derivative of cosine is negative sine, so that's the second derivative of sine. The derivative of negative sine is negative cosine, so that's the third derivative of sine. The fourth derivative of f is the derivative of negative cosine, which is sine, again, because it's negative sine, so it's just sine. The fifth derivative of sine is the derivative of sine again, which is just cosine of x again. Now let's evaluate those derivatives at 0. Well, f of 0 is 0. F prime of 0, cosine of 0 is 1. F double prime of 0, so what's negative sine of 0? That's 0. The third derivative at 0 is negative cosine of 0, that's negative 1. The fourth derivative at 0 is sine of 0, that's 0. The fifth derivative at 0 is cosine of 0, which is 1. We're seeing a pattern. I mean, what's really going on is that the fourth derivative of sine is itself. So the fifth derivative of sine is the same as the first derivative of sine. It means the sixth derivative of sine is the same as the second derivative of sine. So if we're just looking at these derivatives at 0, we're seeing 0, 1, 0, minus 1, 0, 1. What's the sixth derivative at 0? It's going to be 0 again. What's the seventh derivative at 0? Well, it's got to be minus 1, right? Because it's 0, 1, 0, minus 1. And the fourth derivative is the same as the 0th derivative, right? The fourth derivative is the function itself again. So it's 0, 1, 0, minus 1, 0, 1, 0, minus 1. The eighth derivative at 0 would be 0. The ninth derivative at 0 would be 1. The 10th derivative at 0 would be 0. The 11th derivative at 0 would be minus 1. And it'll just keep on going. 0, 1, 0, minus 1, 0, and so on and so forth. Finding that pattern lets us write down the Taylor series around 0. Well, here's what it ends up being. Or at least this is one way of writing down what it ends up being. So the Taylor series around 0, so centered around 0, for sine is the following. It's the sum, n goes from 0 to infinity, of negative 1 to the nth power divided by 2n plus 1 factorial times x to the 2n plus 1 power. But why does that work? Well, to think about this, I've made this table here. So this is a little table that shows n, and then below here is the nth derivative of sine evaluated at 0. All right, so the 0th derivative is just the function sine at 0. The first derivative is cosine at 0, which is 1, so on. These are the numbers that we computed before. And they've got this pattern that we saw, 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on. But what you should notice is that at all the even derivatives are 0. So this thing doesn't include any terms with x to an even power. And that's why I've written x to 2n plus 1. This is kind of a sneaky trick just for recording all of the odd powers. And what about those terms with x to an odd power? Well, when n is an odd number, I'm flip-flopping in sign, in SIGN. And that's exactly what this minus 1 to the n accomplishes for me. This is all pretty great, but it's raising a very serious question. Is this power series actually equal to sine of x on any interval? That is the problem. We're assuming that sine has a power series representation valid on an interval around 0. And if it can be represented as a power series, then we've figured out what the power series has to be. But how do we know that sine has any power series representation? That's the problem that remains.